Insertion sort. In this part, now we can complete the whole insertion sort. It's pretty easy. We just apply our insertion operation one by one until we get all the elements sorted. So that's simple. Yeah. So let's take a look. Yeah. Estimate efficiency. Yeah. So when we look at the whole procedure, so we can easily also calculate the number of operations we need to do. Yeah. All right. To do insertion sort, basically we just do compare and shift operation. Yeah. All right. So on this array, so you can see when we insert a general k element, so how many comparisons, shifting operations do we need? Yeah. Depends on the location of your new element. So we can consider best case, worst case, average case. 3 possible cases. Yeah. All right. For the worst case, you have to compare a k with all the elements. So that's k comparisons and k shift operations also, worst case. You know. So here, because those two numbers the same, we just combine them, compare and shift as one operation, combine them. Okay, so that's why here I call compare and shift operation. Yeah. All right. So the worst case, when you insert A1, you get a 1, the worst case. A2, you get 2, and so on. The last one, you get n minus 1. All right. So then, by that simple formula, so we get this expression. Yeah. So that's the worst case. Yeah. Next, for the best case, also very easy. For the first comparison, we get it sorted. We only need one comparison. The first one, the new element is greater than the first element. Then we just put it right there, the last position, right? Yeah. All right. So for the best case, we have this formula. 1, 1, 1, total n minus 1. So that is n minus 1. The best case. See, how much is the difference? Big difference. So that's the property for the insertion sort. If you look at the selection sort, bubble sort, we don't have this property, right? Selection sort, bubble sort, the best case, worst case, the same. Here you can see the best case, worst case, big difference. Yeah. All right, so the last one, the hardest. Yeah, so here, if we use asymptotic notation, we have this expression, but the last, most difficult one, average case. Here, I do not do it explicitly. I like to leave it to you as a practice exercise. Yeah. Can you calculate the average case expression? So I need your expression like that. I need expression like that. Although the final answer still this one similar to that one, but the coefficient, the constant coefficient is different. The constant coefficient is different. Yeah. So if you are interested, you can try later at some time. So probably I will do it. All right. So yeah, because it's an interesting question. All right. All right. So now, last thing, conclusion. After we solve this problem, let's make the final conclusion. insertion sort has a very special property. Yeah. How special is its best case is extremely good. You know, the performance of its best case extremely good. Yeah. So worst case, we know, yeah. Worst case bad, but it's okay. You know, we expect that. Worst case, you know, always bad for most of the sorting algorithm. Yeah. But the question is, how do we take advantage of this really good best case efficiency? How do we take advantage of it? Yeah, think about that. Here, I want to describe a special situation so we can take advantage of this best case efficiency. If the given array is almost sorted, okay, then the insertion sort is a good choice for sorting. So this is the way we take advantage of good best case efficiency. Why? Almost sorted, that means it is very close to the best case, right? Very close to the best case. So let me draw a diagram. Suppose this is a given array. Yeah. There are some scattered spots, locations. The elements out of order, yeah, not sorted, yeah, but all the remaining other parts already sorted. Do you think it is pretty close to the best case? Pretty close to the best case. If we apply the insertion sort, then, so let's imagine the procedure. If we apply insertion sort, we can enjoy the best case at the place already sorted. Only when we hit the bump, right? Hit, you know, out of order cluster. So let's go out of order clusters. Yeah. Then we need to do a little more comparisons, shifting operations. Okay. Yeah. We need to do a little more. Okay. Yeah. Scattered locations. We need to do a little more. Okay. Yeah. So you can see the overall performance will be really good. Yeah. Very close to that. Yeah. So that is the conclusion. Yeah. So that is the special property of the insertion sort. Okay. All right. Yeah. So we finish the insertion sort. Yeah. In our last video, I want to use the insertion sort idea to solve some interesting problem. Yeah. So we will see the insertion operation. Although it is very simple, but sometimes it's pretty useful in our 8.4. All right, so let me stop here for 8.3.